Okay, so she's going to talk on conventional and exotic meson spectrum from lattice QCD, and Sinead is from Trinity College, Dublin. So go ahead and get started.
Okay, so thanks very much. Hopefully you can see my slides now in full screen mode. Okay, great, thanks. So first of all, thank you very much to the organizers for the invitation to speak at this workshop. So this is the title that was suggested, and it's obviously quite a broad title, and I've decided to interpret it in a particular way. So I'm going to show you a selection of some work, recent work that's been happening in meson spectroscopy from lattice QCD. So this is by no means an attempt at being comprehensive, but rather somewhat biased, I would say. So here's an outline. In thinking about the talk, tried to provide some motivation, at least in context for the workshop itself, since the discussion is about the standard model and the emergence of mass in the standard model. So I will try to place QCD within that context, and then in particular motivate lattice QCD calculations within that context. And then, as I already said, I'll give a biased selection of results from meson spectroscopy. So you'll see some results from low-lying spectroscopy, where, for example, all of the uncertainties are under very good control, and then more speculative, let's say, and more recent results going beyond ground states, where we think about excited and exotic spectroscopy, and then come to some conclusions and summarize for you. Okay, so since Sebastian wasn't here, I get to show some information about the standard model. I sort of thought he might have already done this, and then I would be repeating, but I don't feel so bad now that this is the first time that we just look at the sort of standard picture of elementary particles in the standard model, which of course, as we know, has been extraordinarily successful to date. Although of course also precision tests of the standard model are more important than ever as we look for signs of new physics. And very often, and we've seen this very recently, that controlling the hadronic uncertainties can often be a limiting factor in these searches for new physics. So within the standard model, so QCD is the only experimentally studied strongly interacting quantum field theory. So this brings with it many subtleties from the effects of that strong interaction. And although it's been studied for many decades already, there are still puzzles and surprises. In particular, for example, the exotic states which have been found recently in the XYZs, as we heard very nicely in the last talk, which are really not understood fully yet. So just by way of reminding you, you can think about QCD, of course, as having two rather distinct regimes in some sense. So at high energies where the theory is perturbative and the quarks and gluons, the degrees of freedom are essentially free. And as the coupling runs at low energies, the theory becomes non-perturbative. And here we have the confinement realized, and the degrees of freedom are can be thought of as instead now the mesons and baryons, which are the observable quantities in the theory. So one question one can ask, and again in the context of this workshop, is how do you go from a theory of quarks and gluons, which is QCD, to the observed low energy hadron spectrum? And so to understand how to do this, one has to think about, let's say, the secret life of hadrons. So hadrons, or the observable quantities of this theory, are the essentially emergent phenomena which result from collective behavior of the fundamental degrees of freedom of the quarks and gluons. So this is dynamical mass generation through the nonlinear interactions that are present in the QCD. And confinement, of course, we know, is a purely quantum phenomenon, and it's not understood in the sense that there isn't a mathematical framework or mathematical proof for this, although its consequences are long established. And for example, through experiment and through lattice calculations, confinement is realized and understood in that way. So there's a very nice discussion, of course, of the state of the discussion of the problem of how to mathematically formulate confinement by Arthur Jaffe and Ed Witten for the Clay Prize. And so rather than trying to think about understanding confinement itself, instead we can ask, if we start from the QCD Lagrangian, which I said on the previous slide is formulated in terms of the fundamental degrees of freedom, can we calculate then from this QCD Lagrangian the full spectrum of allowed or observable states? And so this motivates then this lattice approach, since QCD admits a very rich, and also exotic spectrum. So we have the standard mesons and baryons, but QCD also allows for many other varieties of observable states. Of course, some of them you've heard already discussed by Feng Kuang, but tetraquarks, hadronic molecules, hybrids, and glueballs, for example, and not just in potential model degrees of freedom quantum numbers, but also with manifestly exotic quantum numbers. So this, as I said, is, one can think about this, this part motivates an attempt to understand the spectrum from first principles, which I see I've spelled incorrectly, using lattice QCD. So since I think there are not so many lattice people in the audience, let me spend 1 or 2 slides to just outline for you very briefly, without going into too many technical details, how you take a continuum QCD Lagrangian and realize it then on a discrete space-time lattice, which facilitates numerical simulation. So the first point is that we, of course, start from the QCD Lagrangian, which you can see here, and then one can think of the gluon fields as now the links in this hypercube, which you can see a cartoon for here, while the quark fields live on the sides of this lattice. The discretization for the fermion fields can be done in a number of different ways, and you may be familiar with some of these ideas. So Wilson fermions are staggered and overlap. Of course, in the continuum, as you remove the lattice spacing, then these discretization methods, the observables calculated with these different approaches should all agree, and that's been a topic of some study on the lattice and has been demonstrated for many quantities now, in fact. In the usual way, derivatives are replaced with finite differences. And one point maybe to note here is that in the lattice simulations of QCD, there are essentially 2 parameters, input parameters. One is the quark mass, which appears in the Lagrangian, and the second is the coupling, and that you can think about as the lattice spacing. So the distance between the sites on this lattice, in lattice terminology, it's often written as little a. So the observables for meson spectroscopy, these might be 2-point correlation functions, are then determined from a finite dimensional path integral now, because the theory has been discretized on a finite hypercube. But by calculating the path integrals of this of the finite dimensional QCD, the formulation of QCD now in this finite dimensional way. One last wrinkle is that we simulate or do these numerical simulations in Euclidean time rather than Minkowski time, and that's purely driven by computational necessity to ensure that we can utilize Monte Carlo techniques. The QCD path integral is reflected here, and you can see that again, on the lattice, what essentially we end up calculating are the observables, this curly O, on samples of the background field configurations, and then averaging over those calculations of the observable on the background gauge field configurations. So of course, there are many technical details and huge amounts of work that have gone into understanding how to do this and how to do this properly, but that's the basic idea that you might keep in mind. Then for meson spectroscopy, which is the topic of this talk, we're interested in 2-point correlation functions, and these are built from interpolating operators. So here's again a cartoon of what these might look like. So you, for example, may have a quark and an anti-quark field that sit at the same site, or you may pull them apart and have some distance between the quark and the anti-quark field. And you're free to do that in many and varied ways, as I've illustrated for you here. So we construct then a basis of these operators, which are fermion bilinears. So we have quark field psi and psi bar with some structure in between, where the gamma is the Dirac gamma matrix, and the derivatives D, as I said, can be represented. You can have as many of these derivatives as you like in here to form operators which overlap with the state of interest. Now, again, for the experts in the audience, what I'm talking about at least the results that I'll show you, will be using distillation, which has proven to be really very useful for hadron spectroscopy. And using these techniques, we can build large matrices, correlation matrices of 2-point functions, which you can think of here in this way, and you can write like this, where you have a sum over states, which has some exponential behavior like this. And what you're interested in is the energy of the state n, so En, which is upstairs here in the exponential with some prefactors in front. So of course, if you're interested in the ground state, then in your lattice calculation, you go to large time extents, and you can see that that ground state, which is the lightest state in the system, will be, you can calculate that energy then by exponential fits at large times. However, since we're also interested in excited states of mesons and also baryons, but for this talk, just mesons, then instead of simple exponential fits, we solve a generalized eigenvalue problem, which you can see represented here. And then the eigenvalues that you extract in that from that eigenvalue problem, essentially by diagonalizing this correlation matrix that you've made, these eigenvalues contain information about the energy of the state that you're interested in. So from the eigenvalues, we can extract energies. From the eigenvectors, which of course you also get in the same calculation, we also know that these are related to the operator overlaps, and essentially they carry information about how much the operator that you've constructed overlaps onto the state of interest. And so it turns out, without again going into too many details, that we can use these operator overlaps in a very informative way to help us to do spin identification in our lattice calculation. So it's maybe useful, especially for the non-experts, for the non-lattice people, to think about what we've just done in the previous two slides, and in particular for spectroscopy, what the consequences of some of the compromises that one has to make to perform these numerical simulations. So the first, most obvious, of course, is that we work in a finite box at finite lattice spacing. And so again, this cartoon is to try to show you how we think about this. So of course, we have a lattice spacing, which is denoted with A. And so what you would like to do is to remove that lattice spacing. And the way in which we think about that is by simulating at finer and finer lattice spacings for the same volume, and then performing a continuum extrapolation, which is removing the lattice spacing entirely from the calculation. Alternatively, checking, for example, that the physics that you extract doesn't depend on that lattice spacing. And similarly, one can think of simulating at different volumes where, for example, one may hold the lattice spacing fixed and change the volume of the box and then ask whether there are consequences for the observables that you're calculating, in which case you have some finite volume effects. It turns out that simulating at physical quark masses is a challenge, and that is true whether at both ends of the possible scale of quark masses. So the computational and computational complexity of simulating with physically light quark masses, so U and D quark masses, is a difficult problem. It's been solved, but it's still a costly calculation to do. And similarly, at the other end, for heavy quarks, there are additional technical constraints because discretization uncertainties scale like the heavy quark mass. And so for B quarks in particular, these uncertainties can be large. I would say that in both directions, there's been a huge amount of progress, and now physical light quark simulations are possible, and certainly heavy quark systematics are well understood and controlled in most calculations now. Just a point here very briefly that, as I mentioned earlier, we now have discretized the continuum to a hypercubic grid. And so the Lorentz symmetry is broken at finite lattice spacing. And so the relevant symmetry groups, in particular for spectroscopy, then are the symmetry groups of the cube rather than the continuum symmetry groups. And an additional piece of work is required to understand then how to map the states that you extract, which satisfy or obey the symmetry group of the cubic symmetry group had to map those numerically determined states back to the continuum. And then finally, as I said, we do a Wick rotation to Euclidean time to enable the Monte Carlo calculations. This has additional consequences. So for example, on the previous slide, you saw that the 2-point correlation function can essentially be mapped onto, or behaves as an exponential, a tower of exponentials essentially. And that's as a consequence of that Euclidean time, but also we lose direct access to scattering matrix elements. And we have a workaround for that, which you will see in the later slides. Okay, so this is a quick summary. This is actually quite an old plot now, but this is to show you that, so the two input parameters that we have, for example, are the quark mass and the lattice spacing. And indeed, if the real world is down here in terms of the pion mass at 0 lattice spacing, here's a selection of lattice calculations. This has certainly been updated in the intervening years since this plot was made already a couple of years ago. So for example, we can simulate at the physical pion mass, which you can see in these points here, but also below the physical pion mass as well, and straddle that point. And you see that there are many calculations over a range of lattice spacings as well. Okay, so let's turn now and look at some results. So this is now at the conventional, let's say, meson spectroscopy side of things. So here's a very beautiful calculation of the light hadron spectrum. This is to highlight for you that precision ground state physics from lattice QCD really now is very well established. This is from the BMW collaboration. And you can see a very beautiful precision realization of the low energy spectrum. The points are the lattice measurements, and the lines are the experimental results with some width where that's relevant. So for example, for the row where the width is given also by experiment. And you can see also, so in this calculation, they have really taken care of all of the uncertainties that arise as a result of the discretization and the numerical simulation, and have really a very beautiful determination of this spectrum. But one can go a little bit further and include, for example, QED effects. And so this is the very beautiful calculation also from BMW of the neutron-proton mass difference. So these are really rather tiny effects that one is calculating. And you can see again from the red dots, which are the lattice calculations, that very precise and very accurate results are possible. So this is very much in the sense of a conventional spectrum, but very important to demonstrate that this can be done precisely and accurately from lattice QCD. If one looks beyond ground state, so this is back to the earlier slides, thinking about now excited states and indeed exotic states in the light sector. This is from the Hadron Spectrum collaboration already quite a few years ago. And this is a very busy plot. So maybe just to take away from this, there is a plethora of states which have been determined in this lattice calculation. So the gray bars, the green and black bars, these are all lattice results at different quantum numbers, which you can see underneath in the negative parity sector and the positive parity sector. And indeed also including states which have manifestly, explicitly exotic quantum numbers. So these are not found in potential models. The height of the bars is a measure of the statistical uncertainty in the calculation. But again, this is a rather different calculation to the BMW result. So you see that the pion mass in this calculation is quite heavy. It's not a physical pion mass. This is performed at a single lattice spacing, for example, also. And so here you have an example of a very extensive spectrum calculation, but one which has, again, unquantified systematic uncertainties, because instead what's been demonstrated is the ability to extract these highline excited and exotic states. So the next steps, of course, are improvements in terms of pion mass and finer lattices and all of those things. However, one can also extend the same methodology beyond the light sector. And so this is into now Charmonium, into heavy quarks. So in Charmonium, we have done, as part of the Hadron Spectrum collaboration, again, already quite an old plot now, also from 2012, I believe, a very extensive calculation of the Charmonium spectrum. again, you can see that the continuum quantum numbers are given along the bottom here. And so we have circled here, you can see on the plot just circled, for example, S waves extracted, also P waves and excited P waves, D waves and F wave, and many states in these different channels, including, again, on the far right side over here, some exotic states with exotic quantum numbers. So there, again, are many uncertainties. As you saw on the previous slide, all of the same caveats from the previous slide apply. It's also the case, and I should have mentioned that in the previous slide as well, that the assumption here is that everything looks like QQ bar. All of the states are determined using operators that are QQ bar or QQ bar with some gluonic content for their hybrids. But of course, as you go above threshold, then this is not a full recognition of the dynamics of the system. And so some resonance and scattering is more appropriate at that point. But this is a demonstration, at least, that these Highline states can be extracted. Apologize if you can hear the noise in the background. Somebody's decided to move some office furniture nearby. Okay, so there's exotic the excited and exotic spectrum then was extended more recently to Botamonium. So very similar methodologies used from light to charm to bottom. And here again, you see a very extensive spectrum has been extracted in a lattice calculation. So the boxes are again the results from the lattice calculation, and the height of the boxes gives you an estimate of the statistical uncertainty. And so here again, you can see the continuum quantum numbers, and over here you see the states which have exotic quantum numbers, and so these are quite high lying and include, according to the color coding, which may be a little bit hard to see, I apologize, it's quite small. So the red and the blue colored boxes are states which we identify to have non-trivial gluonic content and identify as hybrid states in the spectrum. So you see that there are quite a few of them scattered around. So in particular, they are here with exotic quantum numbers, but also appearing in the non-exotic channels, conventional quark model channels, here in red and also high in the spectrum, highlighted in the blue color. So maybe let me pull these out from the Charmonium spectrum to just highlight a little bit more what we can determine in this lattice calculation now for hybrid mesons, including exotic quantum numbers. And you see in both red and blue, these hybrid states highlighted in this spectrum plot. This is in Charmonium. We see very similar results in all of the different sectors where we've made calculations, in particular in the light sector, although I haven't shown that to you here, and also in Botamonium, which I also haven't shown you, but the picture is very similar. So in particular, what seems to happen is that the hybrid states emerge in the same pattern. So in these multiplet patterns, this is a hybrid supermultiplet, as we call it, and at the same energy scale, at around 1.3 to 1.5 GeV above the lightest state in the system. So here above the eta C in the Charmonium system, at a similar scale in Botamonium and also in the light sector. So it seems to indicate that there's some common phenomenology for these hybrid states in QCD, and the way in which the mass these states emerge from the gluonic degrees of freedom seems to be replicated as you go through the different sectors from light to heavy. But let's take a couple of minutes maybe just to go beyond these bound states. So everything that I've told you, all of the results that I've shown you so far have used or assumed QQ bar type operators and bound states. So even as you go above threshold for those high states, there hasn't been any resonance physics or any attempt to include the physics of multi-hadron states. But in principle, sorry.
Minutes.
Hello?
Minutes for the rest of your presentation. Okay.
Sorry?
Minutes.
Okay, yep, thanks. Yes, sorry, that's great, thanks. Sorry, I just couldn't hear you. So let me just say, beyond simple bound states then, again, the lattice people, of course, will know this very well, but maybe let me just point out the real problem is that we've lost direct access by Wick rotating to a Euclidean field theory to the scattering information. This was understood by Lucier some time ago, how to relate the information, the spectrum that you extract on a lattice volume, a discrete volume, to the continuum phase shifts through a relation which is given here in the rather simplified case. So essentially what's happening is you map from a lattice calculation at different volumes L into a continuum phase shift, which obviously the more points you have in your lattice calculation, the better you map out the phase shift in and the resonance behavior in the continuum. But this is now working very well. Again, this is a conventional, let's say, example where we just looking at pi-pi scattering, and this is the row resonance, which has been extracted very beautifully in lattice calculations at 2 different pion masses. And as you decrease the pion mass to go from the sort of blue color to the red color, you see that the resonance behavior becomes more like the continuum behavior in a very, very nice way. And maybe let me just highlight that the secondary effect that we have here is that we can use the lattice then as a tool to study mass dependence, since the mass is an input parameter in these calculations. And so we can dial it up and down to understand this behavior. And we can do more interesting or more exotic states, including isoscalar pi-pi scattering. So this is the sigma meson, which again, for 2 different pion masses, and you can see that it evolves from a bound state below pi-pi threshold. So that's the green curve that you see on the plot up here, to a broader resonance at lighter pion masses. Again, mimicking the, becoming closer to the shaded gray points, which are the experimental data points for this state. There's lots of technical improvements that were required to make these calculations, and I won't go into the details here, just to say that this sort of scattering calculation in these conventional channels is under control. But now, of course, we would also like to understand how the resonance physics works in exotic channels. And here's a very recent first attempt at that. So this is the exotic 1 minus plus pi 1 hybrid meson in a couple channel analysis at rather unphysical parameters, so at the SU3 point. But this is nevertheless the first demonstration of this sort of resonance physics from a lattice calculation for manifestly exotic quantum numbers. So if there are, they find that the pi 1 is a narrow resonance at these rather heavy pion masses, and then having attempted a crude extrapolation based on some couplings, they can suggest that the resonance broadens at lighter pion masses. So this is a really very beautiful result, and one can think about this towards a phenomenology of hybrid decays, really starting from first principles from the QCD Lagrangian and now deriving the properties, resonance properties of these exotic states. So for the first determination, as I said, in the light sector, one would obviously like to think about this in heavier quark mass systems. So I have really very little to say on this. This is an open question on exotic quaconium-like states, and we heard in a very nice talk just before mine how one might tackle these so-called XYZs. So let me just show you the sort of standard plot, which shows you how many unexpected states have been found. So these are the sort of salmon color and magenta colored boxes in the Charmonium spectrum. So this strong exotic matter has been around now for of the order of 15 years, and it's still not properly understood. From a lattice perspective, one has to understand the resonance physics that and how to calculate that on a lattice, including multi-hadron operators, tetraquark operators, as well as the standard QQ bar operators. It's also the case that lattice studies of strong decays, so radiative decays, for example, of the hybrid states may be very useful, and that's certainly something that's underway at the moment. But there are many new difficulties, and the reason progress is quite slow for lattice calculations in this sector is that heavy quark mass brings with it particular challenges, and one challenge in particular, as well as the technical challenge of simulating the heavy quark, is the proliferation of thresholds which open up in Charmonium and Botamonium systems, and which should be taken into account in any sort of sophisticated calculation. So this remains an open challenge. There's been a first look of course, others. I've picked one from HadSpec, which is the charm tetraquarks in both hidden charm and doubly charm. So you can see here for isospin 0, a selection of states that have been calculated in the lattice calculation. These are the boxes in different channels corresponding to different continuum quantum numbers. This is again done with rather unphysical pion masses, but done in both isospin 0 and isospin 1, although no obvious signs of a resonance have been found, at least with this simulation. So this is, let's say, a first look at how one might calculate or extend the basis beyond this Charmonium spectrum that I showed you some number of slides ago to a more realistic inclusion of meson, and tetraquark operators for this sort of physics. But since I'm out of time, let me just say that QCD describes the properties of observed matter in terms of fundamental variables, and lattice offers a potential to, from first principles, make those sorts of calculations. So I haven't discussed many things here, so I will just leave you to stare at those and just say that many open questions and unsolved problems remain, but there's been significant progress in this spectroscopy arena. And so we're gaining insights into this strong dynamics and into the emergence of mass, hadronic mass in particular, from fundamental degrees of freedom. So I'll leave it there. Thank you very much.
All right, thank you very much. That's a very interesting talk. And obviously you've just sort of touched on a lot of things. I'm sure there's a lot more underneath the surface that we could go on about. And maybe in the discussion section, we can come back to some of these things.
Happy to, yep.
Yeah, so I don't know if there's too much time left, but I think if there's one or two questions out there, I'd love to have the chance for people to ask them. All right, if there's no questions, thank you, Sinead, for a very nice talk.